Good morning, everyone. Sounds maybe a bit loud. You can hear me in the back okay? All right. So, good morning. Thanks for getting up on this relatively chilly Wednesday morning and making your way in. Before we get started, does anybody have any questions on anything we've been talking about, the term paper, other things? Okay. If not, then just as a reminder, as of noon yesterday, the term papers for you to review should now be available. If you go in, so go to the assignments term paper folder, the same portal where you submitted your first draft should now be the portal where instead of being able to upload a submission, you're going to see here the 4 papers that were assigned to you. And I believe we set the deadline for completing those reviews as next Wednesday by end of the day. So you've got about a week to read through those 4 papers and offer some constructive and some substantive criticism. What do I mean? Constructive, if the author takes your criticism and works with it, it should be able to improve their paper. You know, so, oh, well, I thought this part of the discussion was a little bit confusing. Maybe adding another example would help. Something like that. That's a constructive criticism. And when I say substantive criticism or substantive comments, what do you think I mean? I want to see more than just great job. You know, so that when we're going through and looking, is it clear to us from the comments that you left that you actually read the paper? You didn't just sort of go through and say, great job, great job, great job, 4, 4, 4, 4, 4, and move on with your life. That's not particularly useful to the author of the paper when they get the comments back next week. Okay? So any questions on how that procedure is going to work? Okay. Then maybe for the last announcement, some point over the weekend, it may be later tonight, it probably won't be till tomorrow or Friday, I will post the next homework assignment for our search engines unit, and at that time I'll figure out when it's due and when the quiz is going to be. I haven't looked that far ahead on my calendar. And then just remember for your public service announcement, you get an extra hour of probably not sleep, but hour of something this weekend. Do not show up at 8:30 a.m. daylight time on Monday. Show up at 8:30 standard time on Monday. If you show up at 8:30 daylight time, the room will be locked and I will not be here. Okay? So enjoy your extra hour this weekend. Other questions or any comments, ideas? Okay. Then if not, we will pick up with where we were last time. So remember, last Wednesday, when we started talking about search engines, where we sort of finished our lecture was with this introduction of thinking, well, what are algorithms and how do we think about algorithms? And we saw that there were basically 4 common steps that a lot of algorithms were using. So we were talking about algorithms because, number one, we could view a search engine as an algorithm. Because of the total amount of information on the internet, and because of how rapidly it's changing or being updated or being modified, we needed to have some autonomous unit that was able to actually go through and parse all of the internet, at least as much as possible, to see what information is available and how do we index it. We had these things called web spiders or crawlers or bots that would go through, and they're basically executing these algorithms, these step-by-step self-contained procedures to go out and look at a website, catalog that website, and figure out what website to look at next. And so when thinking about algorithms a little bit more deeply, we find that there are sort of these 4 common steps. And I'm sure if some of you have taken some good computer science courses or whatnot, you could probably come up with a 5th step or a 6th step. But most algorithms, everything you're going to do falls into one of these 4 things, where we have something like a procedure, which is actually doing something. You know, maybe as we've got here on the slide, add 2 numbers or compare 2 numbers if we were thinking about that selection sort example we worked through last time. Algorithms can make decisions, use whatever information we have available to us to decide what do we do next. Okay? We can have loops where we want to repeatedly perform a particular step. So maybe we want to perform the same fixed set of procedures and decisions some set number of times. Or maybe we're going to combine it with a decision and say, keep doing this until something happens. Okay? And then last, we can have recursion, where we can think about breaking up our problem, whatever it is we're trying to solve or do with this algorithm, into smaller versions of that same problem, solve those, and then combine the solutions back into the solution of our bigger problem. Okay, and so as we're sort of moving today towards algorithm analysis, understanding how these 4 steps are used in our algorithm, where they appear, what they're trying to do, is going to help us understand the algorithm better. Okay, so then last time we took a little bit of a break from all of this, and we did sort of, in the beginning, sort of stupid Google tricks and saw some neat things that we could do. And in the back half, we had a little bit of a discussion about recipes or algorithms in real life, and we looked at the recipe for chocolate chip cookies. Okay, so why did we do that? So we had this recipe written here. There's all of our ingredients on top and the actual recipe and text on the bottom. But those steps for the recipe were written for a human, which is to say, were there implied steps in that recipe? Yeah, what were some of those implied steps where it wasn't actually written out in there, but they were important things to do nonetheless? Okay, so maybe we had a different ingredient. We had to open the ingredient. So we wanted to pour some oil out, but we had to open the oil first. Yeah, that's an implied step. That does not tell us in this example to do that exactly. Okay, so we have to actually measure something. We don't just say, oh, immediately, oh, there's the teaspoon of salt and just put it in. We had to sort of measure something out. Absolutely. Yep. What was that? Oh, yeah, go out and buy the ingredients and make sure you have all of them. Yep. Okay, pour the batter into the pan. Absolutely. It doesn't actually ever say to do that in here. We had another example of preheat the oven. Unless we just wanted to wait for 20 minutes when we're done mixing up the batter while the oven heats. Can you think of any others that we had last time? Okay, yeah, don't just drop the egg, like shell everything into the batter. You got to crack the egg and get the yolk and the white out. Okay, there's another somewhat important one that I liked at the very end, which was to say use oven mitts when removing the cookies from the oven. Is that important? Yeah. If you value having fingertips, yes. Okay. So there were all sorts of these implicit steps. And if we're thinking about trying to analyze algorithms, sometimes we're going to have to look for these, where we're going to sit down on paper and say, well, here are the steps that we wanted to do to solve whatever our problem is. But sometimes these implicit steps get in the way. And can that complicate analysis of the algorithm? Yeah. If we want to go then and think about telling a computer how to do this, are these implicit steps important? Yeah. Computers are really stupid. We discussed that a few weeks ago. And they don't know the implications. They don't infer things. The computer's going to do exactly what you say. And so if we had on there, put an egg in the batter, it's going to take the egg and it's going to drop it in the batter, which is probably not what you were looking to do. That is to say, the computers don't know what you mean. If anyone's got either really little siblings or nieces or nephews that are a little bit younger, computers are kind of like the 3 or the 4-year-old. They don't pick up on those subtle things that are implied. The fun story, when I was 4, my dad bought at the time what was a $900 VCR, because it was a brand new technology. And it always told me, if you're curious how something works, take it apart and put it back together again. So he comes home from work one day, and my mom's sitting at the kitchen table, just with a snide look on her face. And my dad goes, so what happened today? Oh, you should ask your son. So what happened? So I go running up. Oh, Dad, look, here are the 5 extra parts. 5 extra parts to what? Oh, the VCR. I was curious how it works, so I took it apart and put it back together again. You showed me where your screwdriver was the other week. As he's about ready to go ballistic, my mom's like, oh, no, I've been telling you. You keep telling him, if you're curious how something works, take it apart and put it back together. You need to be more explicit. Okay, so the cool thing was the VCR still worked. The rewind function didn't. Never got that to work again. But when you're thinking about algorithms and you're giving instructions, you need to be explicit when working with computers and with doing this analysis, just as you would when talking with a 4-year-old. Okay? And if you haven't had to try to give instructions to a 4-year-old, just wait. Have fun with that. Okay, so we've now sort of seen, we've got those 4 steps. We've got these idea of what are procedures, what are loops, what are decisions, what's recursion. Have we seen these in action, in examples throughout the semester so far? So in our recipe example from last time, can you think of any procedures or loops or decisions or recursion that entered in to that example? Can you think of any? Okay, so we needed in the recipe, I think it was 3/4 of a cup of sugar, but I don't have a 3/4 cup measuring cup. But I had a 1/4 cup measuring cup, so we could just use that 3 times. That's an example of a loop, because we said we had to do this operation, measure out the 1/4 cup of sugar 3 times to get the appropriate amount. Absolutely. Can you think of any other procedures or other loops or decisions that were made in the recipe example?
Could it be considered a loop of how we beat numerous eggs in?
Okay, so could it be a loop? Yeah, absolutely, of how we beat the eggs in. You bet. Because it said, you know, add the 1 egg and mix, and then add the 2nd egg and mix. So again, add eggs, we're going to do it twice, but we basically did the same operation just twice consecutively. Absolutely. That would be another great instance of a loop. Okay, so we had to make a decision when we were mixing things together. Was this sufficiently well mixed? That's a decision. If it is sufficiently well mixed, we can stop mixing. And if it's not sufficiently well mixed, we should keep going. Okay, so that's a decision. Also possibly with a loop as you're sitting there sort of mixing around, keep going again and again and again. Could also maybe have a decision when the timer goes off and the oven is done, were the cookies actually done? If they're not, leave them in the oven a little bit longer. Okay? So we've seen some decisions, we've seen some loops. Were there any procedures in our algorithm? Were there any procedures that we had to follow when we were actually making those cookies? Yeah. So could a procedure be put the dry stuff in the wet stuff? Yeah, sure. So a procedure could be measure the 3/4 cup of sugar. Okay, so we had to do a loop to get that with the instruments we had at hand, but that procedure of add the sugar to the batter, that's a procedure. Okay. Can anybody think of any recursion that we might have had in our recipe? Did we somehow to make a smaller batch of cookies and then use 2 smaller batches of cookies to make a big batch of cookies? Or does that seem sort of crazy? That seems a little out there. Okay, so I wasn't actually able to come up with any recursion, but sort of as we said, there's some procedures, we had some loops, and we had some decisions in there. Think back a few weeks when we were talking about our data security unit, and we had this idea of Euclid's algorithm, which was used to find the greatest common divisor of 2 numbers. Can you think of any of the steps? Were there procedures or decisions or loops or recursion in that? Anybody have an idea? I'll throw you a bone that most every algorithm has a procedure, because if it didn't, it wouldn't actually do anything. Okay? But can you think of, so what was maybe a procedure that we needed in Euclid's algorithm? Anybody remember Euclid's algorithm? We had sort of the greatest common divisor of 2 numbers. It's equal to the greatest common divisor. We would switch the order and do something like that. Are there any, do you see any procedures that we would have to do as we're working through this algorithm? Right, so one of the procedures would actually be having to calculate what is A mod B. That's a procedure. That's go do something. Okay? Are there any loops in this necessarily? Not really. I don't see any. Any decisions that had to be made? Any point do we have to start to say, well, if something, then something, or something else? Okay, so maybe which one is bigger when we were initially starting, but past that, there's not really. Instead, what we sort of have is, notice, we now started with this problem of find the greatest common divisor of 2 numbers, A and B, which could both potentially be fairly large. In the process of doing this, what we can say is, well, then that's equal to the greatest common divisor of one of those numbers and nominally some smaller number. So we're now saying we can do the same procedure, the same algorithm, on a smaller set of numbers. And that's going to help us get the total answer. This starts to sound a little bit like recursion. Okay? Because we're saying take this one algorithm, this one procedure, for a big problem, and by solving a smaller problem of the same type, we can get the solution. Okay? So maybe there's actually a little bit of recursion here, and we've already, in fact, seen that. So sure, we can do that. And so we could keep applying that greatest common divisor formula, that Euclid's algorithm, until we got down to one of those base cases, which in our case was, it's trivial to see what that greatest common divisor is. When we get the numbers sufficiently small that it's easy to sort of eyeball and look at and see. And in that sense, maybe that's a decision. When is it small enough that we can eyeball it? Okay? And so now thinking towards the example at hand, as we're thinking about how do we sort all of these different web pages. So our search engine has gone and using its algorithm constructed this catalog and this database of all of these different websites. We now issue a search term and it tries to associate to each one of those websites how likely is that site going to be relevant to what you searched. And now we need to sort all of those pages so that either Google or Bing or whatever search engine you're using shows you at the top what is the most relevant page. What's the second most relevant page? What's the third most relevant page? And so we looked at selection sort last week to see how do we actually go about sorting these, and what were some of these algorithmic operations? Did we have procedures in the selection sort? If so, what might an example be? Did we have loops? Did we have decisions that had to be made? What do you think? What was a procedure that we needed when we were doing selection sort? Procedure can be any sort of do something. What was the thing we had to do as we were looking through that list of numbers, trying to figure out what's the biggest one and what's the second biggest one and the third biggest one? Okay, so we had to find the largest value. That's sort of what the algorithm was actually doing. So that maybe we can break it down into some more specific steps. But what was sort of, what's that innermost kernel? What is it we were actually doing at any point in time? We would have two numbers, and we had to figure out which one was bigger. Comparing two numbers, is that a procedure? Yeah, that's do something. And so then right after we were done with that, we might have a decision to make. Well, if one number is bigger, we do one set of operations, versus if the other number is bigger, maybe we either just ignore it or we can do some other set of operations. And were there any loops involved in selection sort? Did we have to sort of keep doing something until something happened? Yeah, keep going through the list and finding that biggest element until we've got nothing left to go through. Okay? So we can sort of see all of these procedures, loops. I didn't put decisions here. But there were decisions as we were looking at each of those numbers to try to track what's the biggest number we've seen so far. But we can start to see and formulate this algorithm in terms of those four key algorithmic steps. Okay? Any questions sort of on these examples before we move on? But this is sort of where we're going. And how do we think about algorithms require sort of breaking apart what we're doing into these really basic steps. Okay? And so one thing that can be somewhat nice when looking at an algorithm is to try to get some sort of graphical representation of the algorithm. Okay? So the way this is usually done is called a flowchart. I'm guessing you've all seen one at some point in time. I'll just put as a note here, there are standard notational conventions for drawing flowcharts. We're not going to get into them here. But if you want some information, the Wikipedia page here is a good starting point. And one of the examples that they have is for an algorithm on how do you fix a lamp. So suppose you go back to your dorm or go home later, and you go to turn on the light because now, of course, it's getting dark at 6 o'clock, and just wait till next week. And you go and you hit the switch on the lamp, or you turn the knob, or whatever the case would be, and the light doesn't turn on. Okay, so maybe we're now at our starting point. Our lamp doesn't work. And so notice we've sort of got this starting point here up at the top. Okay, so we can see now there's an arrow to another box. Okay, so we have some box here, and there's an arrow in another box. This kind of looks like, what does this flowchart kind of look like? Looks like a graph. In particular, it looks like a directed graph. Okay, where now each of the vertices is some action or some question, some step in our algorithm. And the edges tell us what's the order that we might want to execute them, and what are the possible actions available to us. So we can start, our lamp doesn't work, can follow our graph down, and so we might ask, is the lamp plugged in? Okay, who thinks this is sort of crazy that you would have to ask this? Okay, it's a reasonable question. If anybody's ever worked tech support, I did for a little bit when I was in high school at the beginning of college, and someone would call in, my computer's not working. First question solves 95% of the issues. You laugh. I'm not. Okay. So is our lamp plugged in? So this sounds like a decision. We have to determine, and we can go look and see, oh, our lamp isn't plugged in. Okay, well then we can make a decision, well, because no was the answer, well then we can plug in lamp. And ideally now the lamp's going to work, because we found there was the problem, we fixed the problem, and now when we go to turn on the lamp, the light comes on. Okay, well suppose the lamp was plugged in, so we can make a different decision and trace our flow chart down. Is the bulb burned out? Okay, it happens a lot less frequently with the compact fluorescents now than it used to with incandescent bulbs. But, oh, the bulb was burned out. Okay, well, if that's the case, we can, again, make a decision. And now maybe what we want to do to get our lamp working is just replace the bulb. Put a new one in, we turn on the switch, light comes on. Great. And, of course, if not, well, then the lamp is plugged in, the bulb isn't burned out. Well, something's wrong with the lamp. Realistically speaking, we might want to repair lamp. More realistically, what you're probably going to do is just go buy a new lamp. Okay, but does this sort of give us a solution strategy to try to fix the problem of the lamp is not working? Yep, and we can see there are procedures, there are decisions. Were there any loops in this algorithm? Not as drawn, but maybe there could be. So maybe the lamp wasn't plugged in. We plug in the lamp and it's still not working. So you can think about there sort of being another edge up here. The lamp doesn't work. Or if you want to be more direct, since we don't need to go check again, is it plugged in, we could just draw an arrow down to, is the bulb burned out? Because it's possible both of those things were wrong. Okay, so we could make it more complicated if we want, and there could be loops of some sort, but not really. So let's do maybe something a little bit more complicated. So the flowchart from XKCD, again, talking about tech support. So notice, as with most flowcharts, you're going to have some sort of clearly defined start. In the last one, it was colored differently. And this one, it's actually just labeled start. And so, the problem here now is you've got some program, I don't know, maybe using Microsoft Word, something else, doesn't matter, and you needed to do something and can't figure out how to get it to work. So suppose you need to save your file, and you can't figure out how to get Word to save because for whatever reason Microsoft has done a system update and now it's not working anymore. That sounds like something Bill Gates would do. Okay, so we can come in, well, start, we can follow our directed graph down, and so we now reach sort of this diamond-shaped vertex, which it usually indicates a decision. Find a menu item or button which looks related to what you want to do. So if we were looking to save a file, what might we be looking for? Well, so there's either, you can go in the, usually in the file menu, there's an option called save or save as. In a lot of cases, there's the little quick button that has the icon of it's an old floppy disk. This isn't an acronym, but now that's this sort of the universal symbol for save, even though no one uses 3.5-inch disks anymore. Okay, so we find a menu item or a button that says save, and okay, so we do that. Next stop comes down, and we have a procedure, and that procedure is click it. Okay, follow it down. Did it work? Well, in this case, if we wanted to just save the file, yeah, that probably did what we wanted to do. Yes, and you're done. Okay, that was pretty easy. We can sort of go through and do other things. Did that button work? Well, let's suppose we clicked print instead of save because, I don't know, we were feeling thrifty. Did it work? No. Okay, so now you go, have you been trying this for over half an hour? No, we haven't been. So we come back up and we're back at this decision. Well, this is now starting to sound like a loop. And notice that it actually forms a loop in the flowchart, or if we want to bring in our terminology from our graphs last unit, it's a cycle. So we now have a cyclic graph where that loop is represented by a cycle. Okay, so find a menu item that's related to what you do. Okay, so just for the purpose of moving on with the lecture, let's suppose we get a different decision. I can't find one. Okay, so here it says, here's sort of a decision. Pick one at random. Okay, it seems like a reasonable strategy at this point. Okay, click it. Done. Did it work? Okay, we can go through this whole same thing. Let's suppose it didn't. We still haven't been trying for more than half an hour. Come back up. Still don't find one that looks related. Pick one at random. I've tried them all. Okay, come down. New procedure, rather than just click the button, because we've tried clicking all of them. Google the name of the program plus a few words related to what you want to do. Follow any instructions. Anybody done this before when trying to figure out how a program works? How many of you this semester on how do I convert something into a PDF file? Anyone Google that? Probably more than a handful of you. Okay. But that's fine. And is Google usually within 1 or 2, maybe 3 links pretty good at answering these questions? Yeah. Okay. So did it work? Yes, you're done. Did it work? No. Now we'll say, hey, we've been trying this over for more than half an hour. Probably. Yes. Ask someone for help or give up. Okay. Pretty straightforward algorithm. And again, where we can break everything down in terms of how do we get this piece of software to work in terms of procedures, click it, Google something, into decisions, either find an item, choose one randomly, did it work, and into loops that sort of keep doing this until we've wasted sufficiently enough time that we're going to go bother someone else. Okay? So we can start to see all of the elements at work. For another joke example, quite a while ago on The Big Bang Theory, I think this was like season 3, Sheldon Cooper came up with an algorithm for making friends. Anybody watch The Big Bang Theory? Remember this episode? And so it starts off. This algorithm gets a little bit complicated, but it's pretty straightforward. So the idea is we're a lonely person and we now want to find friends. We know several people, but we're not necessarily friends with any of them. So how do we engage in a friendship? Okay. Well, you start with place a phone call. We've identified a person who we might want to be friends with, and we should call them. Okay. So are they home? No. Leave a message. Wait for callback. Okay, so here was a decision. Here was a procedure. We actually had to leave a message. Okay. Wait for them to call back. That's kind of like a loop, or a decision. Wait until something happens, even though we're not really doing anything. Come back over. Okay, so if they're home, it just comes right over here to a new action, or we wait for them to call back, and then we're here anyway. Would you like to share a meal? Okay, so this is a question we might ask to engage someone in the social niceties. Okay, we ask the question, and then we get a decision. What is the response? Maybe they said, sure, I'd love to grab dinner. So we go, we dine together, and then we begin friendship. Yay, end of algorithm. Okay. Suppose, on the other hand, that no, they weren't interested in having dinner. Okay. So we could go and sort of maybe have a different way to engage our friendship. Do you enjoy a hot beverage? Okay, again, we can have a decision. What's the response? Yes. We can choose, is it maybe tea or coffee or cocoa, whichever one they want. Have a procedure. Go have tea or coffee or cocoa and begin friendship. And if not, well, now we come in. And so this is actually a plot item in the show. Was this idea of sort of n equals 0, n plus 1, and n greater than 6 in the original algorithm as formulated by Sheldon? Anybody remember? No, he just went straight into this recreational activity. Tell me your interests. So the idea of you didn't want dinner, you didn't want to go grab a beverage. Well, is there something we could enjoy doing together? What are things you like to do? And we'll find one. Okay, so you ask the person, what's one of your interests? I don't know, rock climbing. I think that's actually what they used in the episode. I don't remember. And so the person says rock climbing, and I now make a decision. Do I share that interest? Okay, well, if not, the way this algorithm was originally drawn is it just comes back up here to say, well, tell me something you enjoy doing. Oh, I don't enjoy it. Tell me something you enjoy doing. I don't enjoy it. Tell me something you enjoy doing. And this is going to go on for a while, especially if you have such narrow interests as Dr. Sheldon Cooper. Okay, so they added, so basically, what type of algorithm step is this all involving? It's a big loop. Okay, so, but the problem is it's now loop with a decision. Do we ever necessarily break out of that loop? No. And that's really bad when we're designing algorithms. If you can get into a loop that just keeps going around and around and around and around and around and around and around. This is how you've seen blue screen of death on your computer. This is potentially one way it comes about. Okay, that's bad. And so Howard, being the engineer in the show, introduces this counter to say, well, let's start in the beginning and say, how many different types of interests have we tried? Well, when we first start, we haven't asked about any of them yet. But every time we fail, let's increase that counter such that after 6 unsuccessful attempts to find something of mutual interest, well, then we just choose the least objectionable one. Maybe none of them are good options, but some of them are better options than others. Okay. And so we come down, we do whatever that interest is, we begin friendship, and of course, to exit the loop, maybe we actually did share that interest. Well, why don't we do that together, go into interest, and we begin friendship. Okay. So again, even in something as sort of comical as this example from the Big Bang Theory, we can start to see all of these algorithm steps be put together. We can see procedures in here. Let's have cocoa. We can see decisions. Do I share that interest? And we can see loops. And certainly with a counter here to say only do it so many times. Okay? Any questions about this? And about flowcharts in general? If you're also curious, yesterday CNN had an interesting flowchart on should I wear that Halloween costume, which didn't really have any loops, but had lots of interesting decisions and procedures involved, trying to figure out what is your costume and would it be appropriate or not. I'm sure you could probably Google and try to find it. It was kind of humorous, not as much as they thought it would be, but it was a thing. Okay, so now that we can sort of understand all of these different algorithmic steps and how to visually represent them to sort of see in a nice, clean way what is our algorithm trying to do, we can now start to analyze the algorithms. Okay, so this comes back to the example we had in class last week where we looked at the selection sort and we said, you know, well, when we had, I think it was 100 items that we wanted to sort, how many comparisons did it take us to do that? Okay, and we got something, it was, I don't remember exactly what it was, I think it was about 5,000, maybe a little bit less than that. And then we asked sort of the related question, well, if we doubled the number of websites that we had, and we now had 200 websites, and we needed to sort them by that relevance score, how much time would it take us? And we saw that that cost, when we doubled the number of websites, the cost increased by a factor of approximately 4. So we doubled the websites, but quadrupled the number of comparisons. Why did that happen? And is that necessarily good? When Google, we did the example last time, actually sorted and searched about, what was it, 11 million web pages when we did the sort. Is that going to be a good thing where if we double the number of web pages, we quadruple the amount of operations it takes to actually do the sorting? No, that's going to be horrible. Okay? So there are a couple things we need to do. Now that we can sort of break these algorithms into these steps, we can start to analyze them. But even more importantly, we need to figure out, if we want to say, how do we best design an algorithm, how do we optimize it, we have to have a way to describe what are we looking for. And so what this really comes down to is trying to minimize cost. And before we begin and before we can try to do that, we have to figure out what do we mean when we say cost of an algorithm. Okay? There can certainly be several different ways to quantify cost depending on what you're trying to look at. And there's not really a unique answer. In a lot of cases, what you might want to use is actually just count the number of operations. How many different procedure steps did we have to do while executing the algorithm? Okay? And so thinking back from our data storage unit, this could be how many flops were required, how many floating point operations, additions, subtractions, multiplications, how many of those did we actually have to do during the execution of the algorithm? Because each of those is going to have some cost associated with it. From our example when looking at the selection sort last week, maybe we're just counting what's the number of comparisons that we have to perform. Because again, every time we compare two numbers, we can say that's a procedure, count up the total number of procedure steps that we have. Okay? A different one that we might be interested in, rather than thinking about how much work the computer is actually doing, in a lot of cases, is that actually what we necessarily care about? Do we care how hard Google's servers are working, or do we just care that we get the answer in under a second? We're probably more interested in the latter. We don't really care how many trees their servers kill in the process. Okay? And so maybe what we can define by what we want to measure as cost is what was the time it took to complete the algorithm. From when we got to the start element on that flow chart and actually set everything going, how long did it take for us to get to the end? Okay? And if it could be seconds, it could be minutes, it could be hours, it could be days, it could be weeks. I don't know. That depends on your algorithm and what problem you're trying to solve and how long you're willing to wait. But if we want to start thinking about analyzing an algorithm, this could be something useful to quantify. Going more into the computer again, maybe we want to look at how much memory was required. Again, most of our computers have, well, all of our computers have a finite amount of memory. Some people have more than others. And we can have a really great algorithm that doesn't take that long to execute, has a really good number of operations, but requires so much memory that it just won't run on our computer. So maybe we want to analyze this as well when we're trying to identify what's the algorithm we want to use to solve a particular problem. Okay? And so regardless of which of these metrics we end up choosing, whether it's number of operations, time, memory, you can come up with others if you so chose. What it's going to amount to is we're going to develop what's called a cost function for our algorithm, which says given some problem size, which will usually denote the problem size by just a little n, just by convention, given our problem size, how much does our algorithm cost? And again, maybe cost is the number of operations, maybe it's time to completion, maybe it's amount of memory, doesn't matter, whichever one we've picked. And so this is now something we can analyze, because when we want to look at how good is our algorithm, we're trying to figure out how much does it cost. Okay? A better algorithm conceivably would cost less. Okay? Think of it just like shopping. You want to go out and you're going to go buy, I don't know, we're past Halloween. You want to buy cranberry sauce. It's now November, we can talk about that. Okay, and you know, Stop and Shop has cranberry sauce, and King Cullen has cranberry sauce, and I'd be willing to bet Whole Foods also has cranberry sauce. Which one are you probably going to want to go to actually purchase your cranberry sauce? We're going to go wherever it's cheapest. So we're going to exclude Whole Foods immediately from the consideration. But between King Cullen and Stop and Shop, I don't know, they're probably equally priced. So maybe you look at the sales flyer one week and see, oh, King Cullen has it on sale this week. And you go to King Cullen. Okay? But it's the same idea here. So maybe we've now got multiple algorithms that we can use to solve whatever our problem is. Which one should we use? We need to look at the cost of the different options and try to find the one that's going to cost the least amount. Okay? And so we've actually already seen a cost function. When we were talking about selection sort last week, we could develop our cost function by saying what were the number of comparisons that we had to make. So as we were going through those lists and having all of those numbers, how many numbers did we have to compare to get that list sorted to say, here's the most relevant web page, here's the next most relevant, and so on and so forth. And with n different websites, so n different numbers, it took n times n minus 1 over 2 comparisons. And so that was we could say that's our cost for the algorithm using this cost function of saying how many comparisons did it take. Okay? So as we've said, usually what we're trying to do is minimize costs. We want to use the fewest amount of resources to solve our problem, not because we're stingy, that's true, but just because there's a limited amount of resources. Okay? Let's not be inefficient. So suppose now we have 3 algorithms that all sort our web pages. So our search engine goes and gives these relevance scores. And we now have 3 potential algorithms we could use to actually sort them to find what's the most relevant, next most relevant, etc. And they have these 3 different cost functions. So F1 gives the cost function for algorithm 1, F2 the cost for algorithm 2, and F3 the cost for algorithm 3. 4 different examples here. If n is 2, so this says we only have 2 web pages that we're wanting to consider. One is the most relevant, one is the least relevant. Which of these algorithms would you want to use to actually sort that list? For part B, suppose we had 16 websites. For part C, we had 32. For part D, we had 64. Which algorithm would you use? Take maybe a minute or so and see what you come up with. So if n equals 2, which of these algorithms might you want to use? Maybe you want to use the middle one. Okay, so how would you determine that the middle one might be the one we want to use? Right, so we can look at, okay, so we have these 3 algorithms. Well, the first thing we want to ask is how much will algorithm 1 cost to execute on these 2? So we can just plug in n equals 2. Well, 2 squared is 4 times 4 is 16 plus 1 is 17. Okay, so let's tabulate that value just for the moment. So we had 17. For algorithm 2, plugging in again n cubed, or n equals 2, 2 cubed is 8, so that's 8 tenths or 4/5, plus 1/2. It's less than 17. It's maybe a little bit bigger than 1. I don't feel like doing rational arithmetic this early in the morning without a calculator. What was that? 13 over 10, so 1.3. Good. I'm glad someone else wanted to do that. Okay? And so for our third algorithm, again, we can just plug in n equals 2. So 2 squared is 4 over 10,000, is a pretty small number. Plus 3 times 2 is 6, so this is going to be a hair bigger than 6. Okay? So which of those algorithms would you use in this case? We use the second one, that had the lowest cost. Okay? So if we now increase n and we consider n equals 16, which one would you want to use? Well, we can do the exact same line of reasoning and say we'll plug in 16 to all of those algorithms to say how much will that algorithm cost for this particular problem size. And again, between these three algorithms, choose the one that has the lowest cost. Did anybody actually calculate 16 out in the time? We're not necessarily going to go through it. What we can end up finding is that in that case, that third algorithm is actually going to have the lowest cost. If we then ask when n equals 32, it switches back to the second algorithm. And when n is 64, we actually want the first algorithm. We'll have the lowest cost. So one of the key things we're seeing here is if we have different types of algorithms or different versions of it, the one we actually want to use might depend on the problem size. Okay? Usually what we're going to be interested in, though, is what sort of happens as the problem size gets really, really large. So here we had sort of n equals 2, 16, 32, 64. Are any of those numbers even remotely close to the number of web pages that Google has to sort every time you do a search on it? No. We're nowhere close to, what was it, 10 million, I think, or some thereabouts from last time? Okay? So another thing that we can sometimes do here is actually we can just plot these cost functions and, again, give a nice, very graphical way to sort of see what's going on. Do notice here the vertical axis is actually on a logarithmic scale. So notice, every set unit here just increases the number by a factor of 10. Okay? But we can end up seeing, so we've got in blue here our cost function, the f1, which was, I think, the 4n squared plus 1. Our cost function 2 here in the magenta color, and then that cost function 3 in yellow. And so again, if we want to look at these different values, what we could do is maybe plot or put in n equals 2, which is going to be this point right here, and we can see pretty straightforwardly that function 2 has the lowest cost. Okay? And at 16 over here, we can see function 3, or algorithm 3 has the lowest cost. 32, it's back to function 1. There's this sort of narrow region right here where function 2 is better. And then once we sort of hit, I don't know, around 40 or 42, once we get past that, it looks like algorithm 1 is the one to choose. What do you think would happen if we sort of kept going and we kept making n bigger and bigger and bigger? Is F3 necessarily, do you think is F3 ever going to get better? Probably not. Is F2 ever going to get better? Probably not. So it looks like once we sort of pass that threshold of about 40 or so web pages in this case, we're probably always going to want to use algorithm 1. Okay? And this gets at the heart of what we're doing, is to say that eventually, once n gets really large, f1 has the lowest cost. And so what we might say in that case is, at least again, looking at what happens for these really big values of n, we'll say f1 scales the best. As n gets large, eventually f1 will beat the other algorithms, even though for some small values of n, f1 is actually the worst of the three. Okay? And so this is what we're now trying to get at, because Google has to deal with such a large number of web pages, is how do we identify the scaling? How do we know which algorithm is going to do the best as n gets large? And so what we can appeal to is this thing called asymptotic analysis, where we can look and see what's the behavior of this cost function as n gets large, or as we approach asymptotic values. Okay, so as we put here in the slide, in other words, what is the behavior of the cost function when n is large? why don't we necessarily care about small values of n in general? Do you have any ideas? Well, sort of the practical approach is Google's not sorting 40 web pages. It's not searching 40 web pages. So we probably don't care about small numbers. But the other reason why is, so if we look in here, at this crossover point where F1 eventually becomes best, we're looking at, I don't know, let's say about 5,000 would be our cost. In a lot of cases, if you think about, F1 scaling up where now n is now 1 million, is a cost of 5,000 really all that bad? No. We're probably going to, by the time n gets to be 1 million, we're going to be looking at costs in the billions, if not trillions. And even if we don't choose the optimal algorithm, is a difference of 5,000 in cost versus, I don't know, let's say 1,000 in cost, is that going to be even noticeable to us when we're expecting other cases we're going to be in the trillions of cost? No, we're not going to care. And so strictly speaking, it might be an inefficient choice, but it's so negligible, the difference between the two, that we're just not going to care. Okay? It's one of those, life is too short and we're going to move on with it. Okay? But that's what's going on. So what we're trying to get at now with this asymptotic analysis is we want to try to determine what's the shape of the cost function when n is large. And so what do we mean by shape? That's something of an arbitrary term, but usually what this might be is it something like n squared? So as n gets large, does our cost function look like a quadratic function? Or maybe it's n cubed, it looks like a cubic function. Or maybe it looks like log n, it looks like a logarithmic function. Okay? That's what we're getting at. And so for our example, where we had our first cost function from the last couple slides, we had this 4n squared plus 1. Well, when n gets very, very large, we all know that that 4n squared term is going to come to dominate the 1, such that the 1 becomes such a small part of that total cost that we can basically just throw it away. Once n gets large, so think about, n is now 1 million or 10 million or even 1 billion. What's the difference between 4 times 1 billion squared plus 1 and 4 times 1 billion squared? The difference is 1, and is that 1 going to be a significant part of that number? No, not really. Which is to say, to a really good approximation, when n is large, we can just say that that function is basically just 4n squared. That 1's not really going to make that big of a difference. Okay? And so what we can then do is say that this function, f1, scales as n squared. So it's telling us the behavior of this function when n gets large is it's going to be a quadratic function. If we double n, our cost is going to quadruple. Okay? And so notationally, the way that we would write this is f is this O, it's usually a script O, but it doesn't have to be, O n squared, which is read, this O n squared is read order n squared, the O being sort of a notational shortcut for saying the word order. Okay? Does that make sense to everyone so far? All right. So then, this order n squared, that O n squared, is what's called big O notation. Just formally getting into what it is, and I'm going to state these details in case you're curious. If we're not going to need this level of detail moving on, so if this is a little bit weird, don't worry about it. What it basically means is that once n gets large, we can write our f1 of n, our cost function, is less than or equal to some c times n squared, where c is just some positive integer. Okay? And clearly we can see from the last one where we had, it was 4n squared plus 1, if we choose c equals 5, is 4n squared plus 1 always less than or equal to 5n squared once n is large? Yeah, sure. Can do that. And so that's how we know that this is order n squared. Okay? And so then more generally, we won't necessarily only have just an n squared. We could have some other functional form for n. Like I said, maybe it's n cubed. Maybe it's 2 to the n. Maybe it's log n. We can get all sorts of different things. And so we can say that a particular cost function f is order whatever this other form is, if, again, we can choose some positive constant c and write that our cost function is less than or equal to that c times whatever the form is once n is sufficiently large. So we keep saying this once n is sufficiently large. What does it mean to be sufficiently large? Is this a rigorous definition? No. This is problem dependent. Okay? So if you're wondering, is n sufficiently large, double it and try again. Or add 10 to it and try again and see. And eventually what we'll see is you can make n big enough where you're always going to get sort of the same general approach or the same general trend when describing the shape of these algorithms. You might have to go to n as 10 billion before your algorithm gets sufficiently large. In practice, you don't have to go that high. But that's sort of one caveat. So a couple takeaways, which now these do start to be more important, is when we're talking about big O notation and talking about algorithmic scaling, we don't care about the constants in front. Okay? So notice, what this means is if we were to say we had our cost function was, let's say, 3 times the square root of n for one algorithm, and we had another algorithm whose cost function was 16,3,980,234 times the square root of n, both of them are classified as order square root of n. Now clearly, which of these two algorithms would you want to use? The first one. It's going to have a significantly lower cost, but in terms of the scaling, they're both order square root of n. As n gets large, we're going to see that same shape in our cost function, even though that constant varies wildly. Okay? And as sort of the general rule of thumb, and this is the takeaway from all of this, if our cost function is a sum of terms, so we saw that 4n squared plus 1 in our example, the scaling of f is usually determined by the term that scales worst. Okay, if you really wanted to get into it, you can come up with pathological examples where this does not hold. We will not see any in this class. Okay, and so when we had our 4n squared plus 1, which one of these two terms scales worse? 4n squared or 1? Which is to say, which one of them gets bigger or gets bigger most quickly as n gets large? What's the 4n squared? So what that tells us then is that our scaling is going to be determined by that 4n squared term, not the 1 term. And the 4n squared is what order? Well, we don't care about the constants, and so we just write it as order n squared. Okay? So we have maybe a true or false question. We could have order n cubed and order 3n cubed. Do they describe the same scaling? What do you think? Who thinks they do describe the same scaling? Anybody? Who thinks they don't? Okay, a couple hands go up. So you said they do. Why? Right. So the coefficient doesn't matter, and so it looks like we could probably just get rid of that 3, and we're going to get the same thing. So you said they're not the same.
Yeah.
Why?
Because the 3 would change it would multiply the scaling by every number by 3.
Okay, so it multiply every number by 3. Okay, so just think back just to the real quick example here where we had this formal definition where we said, f is less than some c times whatever the form is. So what this order would be saying, put the pen back on, is that our cost function f of n is less than or equal to cn cubed, where c is some arbitrary positive integer once n gets large. And what this is saying is that f of n is less than or equal to 3c n cubed once n gets sufficiently large. Since c is some arbitrary constant, suppose c equals 3 would work over here. Could we choose maybe c equals 1 over here and it says the exact same thing? Yep. So are these the same or are they different scaling? They're going to be the same. Okay? Because as was said, the constants just don't matter. But this is why the constants don't matter. We have that arbitrary c, and if we were to throw the constant in front, we could just change our value of c. Okay? And so in this case, you would never see that order 3n cubed in practice. People would just write it as order n cubed. They typically just choose the constant 1 because it keeps things simple. Okay? And that's sort of what that says. So now when we're comparing our different cost functions, from our example before, we had these 3 different algorithms. We've already seen and sort of established that that first algorithm scaled as order n squared. What do you think is the scaling of our second algorithm and of our third algorithm? Take a moment and think about it. what do you think is the scaling of our algorithm 2? Yeah.
N cubed.
Okay, so we have one proposition that our algorithm 2 is order n cubed. Okay, why do you think it's order n cubed?
Because it's the hardest scale.
Okay, exactly. So we can notice that F2 is just sort of a sum of terms. So using that rule of thumb from the last slide, let's look at each of those terms independently and see which one increases the fastest. Well, what increases quicker as n gets large, n cubed or n? N cubed. Okay, so that would suggest then to us that as n gets large, this n cubed over 10 term will eventually dominate the n over 4 term. We can then approximate our cost function as just n cubed over 10. And when we think about the scaling, we don't care about the coefficients, so we can get rid of that 1/10, which just leaves us with order n cubed. Okay? Likewise, what do you think is the scaling of algorithm 3? Okay, it's probably going to be 2 to the n. We can do the same analysis. Well, it's the sum of terms. Well, let's look at each term independently. And what grows more quickly as n gets large? 2 to the n or n? Definitely 2 to the n. Okay, so that says now our 2 to the n over 10,000 term will eventually dominate the 3n. We can just get rid of that constant, the 1 over 10,000, leaving us with order 2 to the n, or an exponential type scaling. Okay? Does that make sense to everyone so far? All right. So then, what we now would want to say is we think about as n gets large, which of these three algorithms has the most favorable scaling? Okay. So again, when we're talking about favorability, we want to know what has the lowest cost. So as n gets large, we can look at these three different algorithms and try to determine which one has the lowest cost. Would you necessarily want the one that's order n squared, the one that's order n cubed, or the one that's order 2 to the n? Again, the question here is, as n gets large, which one of them will give the smallest value? You might want the n squared. Why?
Because obviously n cubed probably get a lot bigger, but 2 to the n, but that's going to be bigger faster because u2 to 50 get bigger too, but u5 squared you get 25.
Right. So that's exactly right. You can just sort of plug in increasing values of n and see, well, we know n squared will not get big as quickly as n cubed, as n gets large. And likewise, 2 to the n blows up really quickly. Okay? Because, 2 to the 10th is 1,024, but 10 squared is just 100. So even at just a small value of n equals 10, n squared is already way better. Okay? And so we can go through that and see that it's in fact that order n squared. And this is exactly what we see if we go back to that plot where f3 is 2 to the n. And notice, it might be good for some small values of n, but eventually that 2 to the n term picks up, or takes over, and this cost just starts growing very, very, very quickly. That's probably not going to be a good algorithm as n gets large. There's a short region here in the in-between where f2 is actually really good, or is actually the best. I wouldn't necessarily say it's really good. But eventually we reach some n where even if that is being n cubed scaling, or order n cubed, we eventually will reach some n, again here it's between 40 and 45, where eventually that algorithm 1 has the best scaling. And so what that says when we look at the scaling analysis is eventually we will find an n where algorithm 1 in this case will give us the best cost, simply because it has the best scaling. Again, we might have to go to an n much larger than 40 in other examples to see where is that trade-off, where's that threshold. But what the scaling analysis tells us is that threshold exists. We will find it. And so when we're looking at Google, working with millions or tens of millions or even billions of web pages, we're probably going to assume we're past whatever that threshold is, and we're just going to use the algorithm that scales the best. Okay, so I think what I'm going to do for the final thing today is we'll put up and ask this question. We'll discuss the answers on Monday. But so here's 6 different scalings that we could potentially have. We've got order n squared, order log n, order 2 to the n, order 1, and order n factorial. Everybody knows what factorial is? So it's n times n minus 1 times n minus 2 all the way down to 1. is to try to rank these and figure out which of these is the best scaling or the most favorable scaling, which is the least favorable scaling. And we can start to develop some rules and some ideas then for when we start to think about different types of algorithms, how can we determine best from worst? So I think that's where we'll leave it today. I will post these slides briefly after class. But in the meantime, I believe we have a quiz. So if we will clear off your desks, except for maybe a writing utensil, a calculator, and perhaps a bottle of water, we will start handing that out. So thank you for your attention. Have a delightful weekend, and remember to enjoy your extra hour Saturday night.